September 19th, 1873, St. Louis, Missouri. The engineering report from visiting European bridge specialists would never fully capture what they witnessed that morning. American steelworkers assembling bridge components using methods that defied everything European metallurgy tradition said was necessary for structural integrity. Through the steam and hammering of the Mississippi riverfront, massive steel arches rose with precision that seemed impossible to European observers. No wrought iron, no traditional craftsmanship, no centuries-old guild methods. Yet they built structures with durability that European iron bridges could not match. In European foundries, master craftsmen required weeks to produce reliable iron using techniques passed down through generations. Each batch was essentially handcrafted, different carbon content, different cooling methods, different strength outcomes. Most carried structural limitations only short-term projects could accept. The Americans were operating with manufacturing philosophy the Europeans had never imagined possible: vertical integration, chemical precision, scientific testing of every single piece, quality standards that transformed steel from experimental material to permanent infrastructure. 900 miles from European workshops, the most decisive metallurgical revolution in industrial history was revealing itself, not in superior tradition, not in craftsman intuition, but in the systematic control that connected every ton of Carnegie steel in ways European iron masters never imagined possible. The Mississippi River carved through the heart of America like a commercial death sentence for St. Louis. By 1867, the great city that had once controlled the continent's river trade watched helplessly as Chicago's expanding railroad network strangled its economy. Every month brought fresh reports of merchants relocating north, drawn by the promise of steel rails that could move goods faster than any steamboat. The numbers told the story with brutal clarity. St. Louis handled 60% less cargo than 5 years earlier, while Chicago's tonnage doubled annually. The city's business leaders understood they faced extinction unless they could solve an engineering problem that had defeated every attempt for decades. No bridge crossed the Mississippi River south of the Missouri River confluence. 1,800 miles of the continent's primary waterway remained an unbridgeable barrier between eastern railroads and western expansion. Steam ferries moved trains across the water one car at a time, adding days to transcontinental journeys and costs that made St. Louis routes uncompetitive. The city's merchants knew they had one desperate chance to reclaim their commercial dominance: build the world's first bridge across the most dangerous stretch of river in North America. The Mississippi at St. Louis presented challenges that had broken previous engineering attempts. Spring floods raised water levels 40 feet above normal, creating currents that could snap iron cables like thread. Ice jams in winter formed barriers 30 feet high, crushing anything in their path. The riverbed dropped to depths exceeding 100 feet, requiring foundation work deeper than any structure ever attempted. Steamboat operators, protecting their monopoly on river traffic, had lobbied successfully for height restrictions that seemed designed to make bridge construction impossible. Any span must soar at least 50 feet above the highest recorded flood level, creating clearances that demanded unprecedented engineering solutions. James Buchanan Eads received the contract through a combination of political connections and audacious promises that seasoned engineers considered suicidal. The 47-year-old inventor had never built a bridge of any size, much less attempted to span the continent's most treacherous waterway. His engineering education consisted entirely of salvaging shipwrecks from Mississippi sandbars, work that had taught him the river's hydraulic behavior through direct observation rather than textbook theory. But Eids possessed something his university-trained competitors lacked: absolute certainty that conventional wisdom was wrong. His design proposal shocked the engineering establishment. 3 steel arches, each spanning more than 500 feet, supported entirely by foundations sunk to bedrock 100 feet below the water surface. The center arch would stretch 520 feet, longer than any arch ever constructed in human history. The side arches, each 502 feet long, would create clear navigation channels wide enough for the largest riverboats. Most revolutionary of all, Eids specified steel for the entire superstructure at a time when no major building in America had ever used steel for primary structural support. European-trained engineers declared the proposal a death trap waiting to happen. Professor Charles Elet, designer of multiple suspension bridges, published calculations proving that steel lacked the reliability necessary for public safety. "This metal remains essentially experimental," he wrote in the American Journal of Engineering. "Its behavior under sustained loading has never been tested over periods longer than months. The citizens of St. Louis will cross this bridge at the risk of their lives." The Institution of Civil Engineers in London issued an official statement warning that steel's unpredictable, crystalline structure made it unsuitable for permanent construction. Even Andrew Carnegie, the Scottish immigrant who had built his fortune on iron manufacturing, expressed grave doubts about Eids's steel requirements. At 36 years old, Carnegie controlled the Keystone Bridge Company through shrewd investments and ruthless cost control. His foremen had constructed dozens of iron bridges across Pennsylvania's railroad network, each one built with wrought iron that had proven its reliability over decades of service. Carnegie understood iron's properties intuitively after years of working with the metal, but steel remained a dangerous unknown. The Bessemer process could transform molten iron into steel in 15 minutes, rather than the 2 weeks required by traditional methods. By blasting superheated air through liquid iron, the process burned away impurities that weakened the final product. But the timing required precision that few American foundries had mastered. Cut the air blast 30 seconds too early, and the steel retained too much carbon, making it brittle as glass. Continue the process 30 seconds too long, and the metal became soft as butter. The margin for error was smaller than most craftsmen could achieve consistently. Carnegie faced a decision that would determine his company's survival. The Eads Bridge contract was worth $400,000, more than his total annual revenue. His Keystone Bridge Company desperately needed the work to compete with larger Eastern manufacturers who dominated government contracts. But if the bridge failed, Carnegie's reputation would be destroyed along with any hope of future business. No major steel structure had ever been built in America, and the first attempt would be the most visible construction project in the nation. The chemistry of steel production remained poorly understood even by experienced ironworkers. Some batches emerged from Bessemer converters with strength exceeding the finest wrought iron ever produced. Other batches, processed with seemingly identical methods, crumbled under loads that common iron could support easily. The variables affecting final quality included furnace temperature, air pressure, chemical composition of the original iron, cooling rates, and dozens of other factors that no American manufacturer had learned to control reliably. Winter of 1872 brought Carnegie face to face with the magnitude of his commitment. He sailed to England to study Henry Bessemer's Sheffield works firsthand, watching British craftsmen who had perfected the process through years of expensive trial and error. In the heart of England's steel district, he observed the precise timing that separated success from disaster. The molten iron glowed white-hot as compressed air blasted through it, burning away carbon and sulfur in spectacular showers of sparks. When the flame changed color from orange to blue, indicating proper carbon content, the air blast stopped immediately. Delay meant brittle steel. Haste meant soft metal, unsuitable for construction. Carnegie returned to Pittsburgh convinced that steel could work, but terrified by what success would require. Eids demanded chromium steel tubing, the highest grade ever attempted for structural use. Every piece must be tested to 60,000 pounds per square inch, double the stress any bridge would experience in normal service. One substandard batch could collapse the bridge and kill thousands of people crossing it. The contract was signed, construction began, and Carnegie discovered that he had promised to deliver perfection in a technology that no American had ever mastered. Pittsburgh's skyline transformed in January 1873 as Carnegie broke ground on the Edgar Thomson Steel Works, named after the Pennsylvania Railroad president whose financial backing made the ambitious project possible. But this facility represented far more than another industrial plant competing for market share. Carnegie designed every aspect around a revolutionary principle that would redefine American manufacturing. Control everything, own everything, perfect everything from raw materials to finished products. Traditional steel makers operated as assemblers rather than manufacturers, purchasing iron ore from independent mining companies, coal from separate suppliers, and transportation services from railroad corporations they could not influence. Each transaction introduced variables that compromised final quality. Ore shipments arrived with inconsistent iron content. Coal deliveries contained unpredictable sulfur levels that contaminated the steel. Railroad delays meant materials sat exposed to weather, absorbing moisture that affected furnace chemistry. Carnegie recognized that excellence required eliminating every external dependency. The vertical integration strategy began with massive land acquisitions across 3 states. Carnegie purchased the Oliver Iron Mining Company, securing control over vast ore deposits surrounding Lake Superior that contained the purest iron concentrations in North America. He bought 6,000 acres of Pennsylvania coal fields where seams ran deep enough to supply his furnaces for decades. The limestone quarries that provided flux for the steel-making process fell under Carnegie ownership, ensuring consistent chemical composition. Most dramatically, he constructed the Bessemer and Lake Erie Railroad, a private transportation network designed exclusively to move raw materials from mines to Pittsburgh furnaces without external interference. Alexander Lyman Hawley arrived in Pittsburgh with engineering credentials that commanded international respect and a mandate to build the most advanced steel facility ever conceived. The brilliant American had studied every Bessemer plant in Europe, identifying design flaws that reduced efficiency and quality control. His Edgar Thomson works would incorporate improvements that European engineers had never imagined possible. The plant layout eliminated unnecessary material handling through careful positioning of furnaces, converters, and rolling mills. Steam-powered cranes moved molten metal with mathematical precision, reducing cooling time that weakened finished steel. Hawley's revolutionary insight focused on converter size and continuous operation. European Bessemer plants used small converters that processed 3 to 5 tons of iron per batch, requiring frequent shutdowns for maintenance and cleaning. The Edgar Thomson works featured 10-ton converters, the largest ever constructed Bessemer, capable of producing 15 tons of finished steel per hour when operated continuously. More importantly, multiple converters allowed round-the-clock production without interruption. When one unit required repair, 2 others maintained full output, ensuring the plant never stopped producing steel. The philosophy of hard driving emerged from Carnegie's obsession with maximizing equipment utilization. European steelmakers followed traditional craftsman schedules, shutting down operations for religious holidays, maintenance periods, and seasonal adjustments. Carnegie's crews worked 24 hours daily, 365 days yearly. Furnace temperatures remained constant, converter timing stayed precise, and rolling mills shaped steel beams while the metal remained hot enough to eliminate energy-consuming reheating processes. The plant operated as a single, integrated machine that never rested. Chemical precision transformed steelmaking from art to science through systematic control of carbon content, the critical variable determining final strength characteristics. Henry Bessemer's original process removed carbon by blasting air through molten iron, but controlling exact carbon percentages required understanding that most American manufacturers lacked completely. Carnegie hired German chemists who understood that 0.25% carbon created construction-grade steel suitable for building frameworks. 0.50 carbon produced railroad rails capable of supporting locomotive weights. 0.80 carbon yielded tool steel hard enough for cutting implements. The difference between success and failure measured in fractions that required laboratory analysis rather than craftsman intuition. Production of Eads Bridge. Steel demanded chromium content specifications that exceeded anything attempted previously in American manufacturing. Chromium created a thin oxide layer protecting the underlying iron from moisture and atmospheric corrosion, but the addition complicated every aspect of the steelmaking process. Chromium steel required furnace temperatures of exactly 2100 degrees Fahrenheit, 50 degrees hotter than standard carbon steel. Cooling rates became critical as excessive speed created brittleness, while insufficient cooling reduced strength below acceptable levels. Carnegie's German chemists developed cooling schedules that brought steel from molten state to room temperature over precisely controlled time periods, measured in hours rather than the minutes used for standard grades. Quality testing at Edgar Thomson Works exceeded European standards through systematic examination of every piece rather than statistical sampling of random batches. Carnegie installed testing machines capable of applying 60,000 pounds per square inch to steel specimens, double the maximum stress any bridge would experience during normal service. European suppliers tested representative samples and assumed remaining inventory matched tested characteristics. Carnegie's crews tested every tube, every beam, every structural component destined for the Eads Bridge. Pieces that failed testing were melted down and reprocessed rather than shipped with reduced specifications. The economic results vindicated Carnegie's vertical integration strategy within months of full operation. By late 1873, Edgar Thomson Works produced 10,000 tons of Eads Bridge steel, meeting every specification Eids had demanded. Production cost per ton reached $56, substantially below the $75 charged by British suppliers whose steel could not match American quality standards. Carnegie had proven that American manufacturing could produce superior products at lower costs than European competitors who relied on traditional craft methods and external suppliers. But the ultimate test waited 900 miles downriver, where James Eids prepared to assemble Carnegie's steel into the longest arches ever attempted. The Mississippi River would determine whether American industrial methods could deliver the reliability that European engineering traditions had provided for centuries. Every tube Carnegie's crews had tested would face stresses that no laboratory could replicate completely. The bridge construction would prove whether systematic control of manufacturing processes could create permanence in structures designed to serve the nation for generations. Steel that met specifications in Pittsburgh furnaces must perform flawlessly when assembled into spans exceeding 500 feet across the continent's most dangerous waterway. The west arch of the Eads Bridge rose from the Mississippi riverbed through September 1873 like a mathematical equation written in Carnegie's chromium steel, each tube positioned with precision that would determine whether American engineering could achieve what European tradition declared impossible. The 502-foot span stretched longer than any arch ever constructed, supported entirely by cantilever construction that balanced 1,200 tons of steel in midair above the flowing river 100 feet below. Traditional scaffolding construction required solid foundations beneath the entire structure, but the Mississippi's depth and current made such support systems impossible. Instead, Eids employed cantilever methodology that built the arch outward from each stone pier simultaneously, with massive steel sections extending into space supported only by cables, counterweights, and mathematical calculations that had never been tested at this scale. Each day's construction added weight that increased stress on previously installed components, creating cumulative loading that demanded absolute perfection in every steel tube Carnegie had delivered. The assembly process revealed the precision of Carnegie's manufacturing control through systematic installation of components that fit together with tolerances measured in fractions of inches. Each chromium steel tube weighed between 2 and 5 tons, shaped at the Edgar Thomson Works to specifications that anticipated thermal expansion, structural loading, and connection requirements. Eids construction crews positioned these massive components using steam-powered derricks that could lift 10-ton loads with accuracy sufficient to align bolt holes separated by distances exceeding 20 feet. The mathematical calculations governing arch geometry required that every piece occupy its predetermined position within margins so small that temperature changes could prevent proper assembly. September 19, 1873, brought the critical test of American steel engineering as the West Arch approached final connection. 2 massive steel sections, each weighing 5 tons and representing months of fabrication work, required joining to complete the arch's structural integrity, but morning temperatures reached 100 degrees Fahrenheit, causing thermal expansion that lengthened Carnegie's steel 3 inches beyond the dimensions calculated for 70-degree assembly conditions. The connection piece, manufactured to precise specifications, would not fit the expanded arch segments without forcing that could crack the chromium steel or compromise joint integrity. The crisis demanded immediate engineering solutions that balanced material science against construction physics. Steel expanded predictably with temperature increases, but cooling the massive arch segments required methods that would not damage the metal's crystalline structure or create internal stresses. Eads ordered his construction crews to pour buckets of Mississippi River water over the steel arches, using evaporation to remove heat energy and contract the metal back toward design dimensions. The cooling process required constant monitoring to prevent thermal shock that could make the steel brittle or create stress concentrations at connection points. At 2:30 in the afternoon, with river water still streaming from the steel surfaces, the final connection piece slid into position with half an inch of clearance remaining on each side. The arch had contracted sufficiently to allow assembly while maintaining the structural tolerances Eids's calculations required for long-term stability. 15,000 spectators lining both sides of the Mississippi erupted in celebration as church bells rang across St. Louis. But engineers understood that completing the span represented only the beginning of structural testing that would continue for decades. October through December. 1873 witnessed systematic construction of the central arch spanning 520 feet and the east arch matching the west span's 502 feet length. Each arch followed identical cantilever construction methods, with Carnegie's chromium steel tubes assembled according to specifications that demanded laboratory-grade precision in field conditions. The central arch's additional 18 feet of span created proportionally greater structural stresses, requiring steel components with enhanced strength characteristics that tested the limits of American manufacturing capability. Construction crews developed installation techniques that maximized the performance advantages of Carnegie's vertical integration philosophy. Unlike European steel that arrived with varying chemical composition between batches, every Carnegie tube exhibited identical expansion coefficients, strength characteristics, and connection requirements. This consistency allowed Eids's engineers to develop standardized assembly procedures that eliminated the custom fitting required when working with materials of unpredictable quality. Thermal expansion calculations proved accurate for every component, enabling precise scheduling of construction activities around daily temperature cycles. Skepticism from engineering authorities intensified as the bridge neared completion despite successful arch connections. The New York Tribune published editorials warning that steel remained fundamentally experimental for major structural applications. No steel structure has operated long enough to demonstrate long-term reliability, the newspaper declared. This bridge represents a dangerous experiment with public safety, built on theories rather than proven experience. Even some St. Louis newspapers referred to the project as Eids folly, questioning whether untested materials could support the railroad traffic that would justify the bridge's enormous construction cost. Technical criticism focused on steel's unproven behavior under sustained loading conditions that railroad bridges would experience throughout their service lives. European iron bridges had demonstrated reliability over decades of operation, providing engineering data that supported design calculations with confidence. Steel bridges existed nowhere in the world, making the Eads Bridge a prototype that would generate the first long-term performance data for the new material. Critics argued that using an entire city's transportation infrastructure to test experimental materials violated basic engineering prudence. Professional engineering societies issued formal statements questioning the wisdom of steel construction for critical infrastructure applications. The Institution of Civil Engineers in London published a technical paper calculating that steel's crystalline structure would change unpredictably under repeated loading cycles, potentially causing catastrophic failure without warning. German engineering schools taught that steel required decades of testing before responsible engineers could recommend its use for permanent structures. French bridge builders refused to consider steel specifications for any project where human lives depended on structural reliability. The completed arches stood as monuments to American manufacturing precision, their chromium steel surfaces reflecting sunlight in ways that iron structures never could achieve. Each arch carried the weight of its steel components, plus dynamic loading from wind, temperature changes, and seismic activity that created stress patterns no laboratory testing could replicate completely. The mathematical calculations predicting arch behavior assumed material properties that Carnegie's quality control had delivered, but actual performance would require years of observation to verify whether American steel could match European iron's demonstrated longevity. Construction moved toward completion through winter months that tested thermal expansion calculations, with temperature swings exceeding 80 degrees between summer heat and winter cold. Carnegie's chromium steel contracted and expanded according to mathematical predictions, maintaining structural integrity while accommodating thermal stresses that would have cracked inferior materials. The consistency of steel composition throughout the structure ensured uniform thermal behavior that prevented stress concentrations at connection points, where varying expansion rates could cause component failure. Public confidence in the Eads Bridge required dramatic demonstration that could overcome decades of skepticism about steel construction. But testing a structure designed to carry railroad traffic presented engineering challenges that no previous bridge had faced. Traditional load testing involved static weights that simulated maximum expected loads, but railroad bridges experienced dynamic stresses from moving trains that created vibrations, impact forces, and harmonic resonances impossible to replicate through stationary testing methods. Eids needed proof that would convince both technical experts and ordinary citizens that American steel could support their lives safely. The elephant demonstration emerged from popular superstition that these intelligent animals possessed instinctive ability to detect structural weakness in bridges and buildings. On June 14, 1874, P.T. Barnum's circus elephant walked slowly across the completed Eads Bridge while thousands of spectators watched from both sides of the Mississippi River. The massive animal, weighing 4 tons and representing concentrated loading that exceeded most vehicles, completed the 1,500-foot journey without hesitation or signs of distress. Crowds cheered as the elephant reached the western terminus, but engineers recognized that animal behavior provided no quantitative data about structural performance under designed loading conditions. Scientific testing began 2 weeks later with the most comprehensive load evaluation ever attempted on any bridge structure. 14 locomotives representing the heaviest railroad equipment available in North America crossed the bridge simultaneously, while engineers monitored deflection, vibration, and stress distribution throughout Carnegie's steel framework. The combined weight of 700 tons, including coal and water supplies, exceeded the maximum loading the bridge would experience during normal railroad operations by substantial margins that provided safety factors beyond European engineering standards. The locomotives moved at 5 miles per hour to create maximum dynamic stress on the steel arches, with synchronized timing that concentrated loading at the bridge's center, where mathematical calculations predicted maximum deflection would occur. Engineers positioned measuring instruments at critical points throughout the structure, recording displacement data that would reveal whether Carnegie's chromium steel performed according to theoretical predictions. Steam pressure gauges monitored locomotive performance to ensure consistent loading throughout the test, while telegraph operators communicated real-time observations between measuring stations. Structural response exceeded engineering expectations as Carnegie's steel arches deflected exactly according to mathematical calculations developed during design phases. Maximum deflection at the center of the 520-foot central arch measured 3 7/8 inches under full locomotive loading, precisely matching theoretical predictions based on steel modulus of elasticity values. When locomotives cleared the bridge, the structure returned to its original position with no permanent deformation, demonstrating that Carnegie's chromium steel remained within elastic limits under twice the designed maximum loading. July 4th, 1874, marked the bridge's official opening with ceremonies that attracted the largest crowd in St. Louis history. President Ulysses S. Grant drove the ceremonial spike, completing the railroad deck connection between Eastern and Western rail networks, while 500,000 spectators celebrated the achievement that transformed continental transportation. A 15-mile parade crossed the bridge throughout the day, with participants ranging from military units to school children, each group contributing to dynamic loading that tested the structure under conditions no engineering analysis could have predicted completely. The economic impact became apparent within months as railroad traffic volumes validated the bridge's commercial importance to transcontinental transportation. Freight trains that previously required ferry crossings averaging 6 hours per transit now crossed the Mississippi in 15 minutes, reducing shipping costs and schedule delays that had made St. Louis routes uncompetitive with Chicago alternatives. Passenger service expanded as railroad companies could guarantee connection schedules without weather-dependent ferry operations that frequently stranded travelers for days during winter ice conditions. Technical performance data accumulated through 1875 as railroad traffic increased to levels that provided comprehensive testing of Carnegie's steel under sustained loading conditions. Daily train crossings averaged 40 freight trains and 12 passenger consists, creating repetitive stress cycles that would reveal any tendency toward metal fatigue or crystalline deterioration that critics had predicted. Engineering inspections conducted monthly detected no signs of stress cracking, rivet loosening, or connection deterioration despite loading that exceeded design specifications regularly. Comparison with contemporary iron bridges revealed the performance advantages of Carnegie's vertical integration philosophy and quality control systems. Traditional iron bridges constructed during the same period began showing corrosion within 5 to 7 years of completion, requiring periodic maintenance that included replacing deteriorated components and applying protective coatings to prevent further oxidation. The Eads Bridge's chromium steel tubes showed no visible corrosion after 5 years of service, with the protective oxide layer preventing moisture penetration that destroyed conventional iron construction. Cost analysis demonstrated the economic benefits of building for permanence rather than accepting shorter service life with lower initial investment. Carnegie's steel specifications had increased construction costs approximately 15% above comparable iron bridge estimates, but maintenance requirements remained minimal while iron structures required substantial expenditures for ongoing repairs and component replacement. The total cost of ownership over projected service life favored steel construction by margins that justified the premium paid for superior materials and manufacturing precision. International recognition followed as European engineers studied American achievements in steel bridge construction. The Institution of Civil Engineers in London invited James Eids to present technical papers describing construction methods and performance data that contradicted previous assumptions about steel's suitability for major structures. French and German engineering schools revised curriculum to include American steelmaking techniques that had proven superior to traditional European ironworking methods in practical applications requiring long-term reliability. But success created new challenges as demand for Carnegie steel exceeded production capacity at Edgar Thomson Works. Orders arrived from railroad companies planning bridge construction throughout the expanding Western territories, each contract requiring steel specifications that matched or exceeded the quality standards Eids had demanded. Carnegie faced decisions about expanding production while maintaining the quality control systems that had made American steel superior to European alternatives. Labor tensions emerged as increased production demands required longer working hours and faster pace that strained the craftsmen who had perfected Carnegie's steel-making processes. Workers who had taken pride in producing superior materials began questioning whether expanded production would compromise the precision that distinguished Carnegie steel from lower-grade alternatives. The company's reputation depended on maintaining standards that required time, skill, and attention to detail that became difficult to sustain under pressure for increased output volume. The 1880s brought systematic expansion of Carnegie's steel empire as railroad construction created demand that exceeded the capacity of all existing American steel producers combined. But growth introduced variables that threatened the quality control philosophy that had made the Eads Bridge successful. New plants, additional suppliers, and accelerated production schedules created opportunities for the inconsistency that Carnegie's original vertical integration strategy had been designed to eliminate completely. The transformation of American steel began its final act in 1901 when Andrew Carnegie, at age 65, accepted J.P. Morgan's offer of $480 million for his entire steel empire. The transaction created United States Steel, the world's first billion-dollar corporation, but the sale represented far more than financial consolidation. It marked the end of Carnegie's philosophy that viewed steel production as a craft requiring absolute control over every variable, replaced by Morgan's vision of industrial efficiency optimized for shareholder returns rather than product permanence. Carnegie's methodology had demanded vertical integration that eliminated external dependencies threatening quality control. His companies owned iron ore mines around Lake Superior, coal fields throughout Pennsylvania, limestone quarries for flux materials, railroad systems for transportation, and steel plants designed for continuous operation under scientific management. Every ton of Carnegie steel reflected controlled chemistry, standardized processes, and testing protocols that guaranteed performance characteristics exceeding specifications. Workers understood that their employment depended on maintaining standards that distinguished Carnegie products from all competitors. Morgan's approach emphasized financial engineering over metallurgical precision, consolidating competing companies to eliminate price competition and maximize profit margins through operational efficiency. United States Steel absorbed dozens of independent steel producers whose quality standards varied widely, creating a corporate structure that prioritized production volume over the systematic control that had made Carnegie steel superior to European alternatives. Cost reduction replaced quality improvement as the primary management objective, transforming steel from a precision product into a commodity judged primarily by price per ton. The philosophical shift became immediately apparent in purchasing decisions that abandoned Carnegie's vertical integration strategy. United States Steel began outsourcing raw materials to the lowest bidders rather than controlling ore mining, coal production, and transportation systems that affected final product quality. Iron ore arrived from multiple suppliers with varying chemical composition that required constant adjustment of furnace procedures. Coal deliveries contained unpredictable sulfur levels that contaminated steel unless compensated through expensive processing modifications. Quality control shifted from testing every piece to statistical sampling of random batches, accepting failure rates that Carnegie's methods had eliminated completely. Production processes evolved toward efficiency rather than excellence, as United States Steel adopted basic oxygen furnaces designed for speed rather than precision chemistry control. The Bessemer process that Carnegie had perfected required careful timing and temperature management to achieve consistent carbon content, but newer furnaces prioritized tonnage output over metallurgical accuracy. Steel became standardized to industry minimum specifications rather than the enhanced standards that had made Carnegie products superior to all alternatives. Chromium content, the additive that created protective oxide layers preventing corrosion, was reduced to save costs despite its proven importance for long-term durability. Meanwhile, the Eads Bridge continued demonstrating the permanence achievable through Carnegie's original quality philosophy. Major renovation in the 1920s replaced wooden railroad decking and updated mechanical systems, but Carnegie's original chromium steel arches remained structurally sound after 50 years of continuous service. Engineering inspections detected minimal corrosion on steel surfaces that showed no signs of the crystalline deterioration that European experts had predicted would destroy steel structures within decades of construction. World War II brought unprecedented traffic loading as wartime railroad traffic exceeded all previous levels, with freight trains crossing the bridge at intervals that created sustained dynamic stress on Carnegie's steel framework. The chromium steel arches handled increased loading without structural problems that affected many iron bridges constructed during the same historical period. Government engineers studying infrastructure capacity concluded that the Eads Bridge could accommodate traffic increases for decades beyond its original design life, demonstrating the engineering benefits of building for permanence rather than minimum acceptable standards. Conversion to highway use during the 1960s required structural modifications that revealed the continuing integrity of Carnegie's original steelwork. Engineers examining the bridge during renovation discovered that steel components retained 95% of their original strength after 90 years of service, with corrosion limited to surface oxidation that had not penetrated the protective chromium layer. Modern steel bridges constructed during the same decade typically required major renovation within 15 to 20 years, demonstrating the performance gap between Carnegie's quality standards and contemporary industry practices. The most comprehensive structural analysis in American bridge history occurred in 2016 when engineers conducted detailed inspections of every rivet, tube, and connection in Carnegie's original framework. Advanced testing equipment revealed that 142-year-old steel showed negligible fatigue damage and retained mechanical properties within 10% of original specifications. The protective chromium oxide layer remained intact, preventing moisture penetration that caused rapid deterioration in modern steel structures built without corrosion-resistant additives. Comparative analysis revealed the economic consequences of abandoning Carnegie's quality philosophy for contemporary cost optimization strategies. The original Eads Bridge construction cost $10 million in 1874 currency, equivalent to approximately $200 million in current purchasing power. Total renovation costs over 150 years of service reached $48 million, creating an annual service cost of $387,000 for infrastructure carrying modern traffic loads safely and reliably. Average modern bridge construction costs range from $50 to $100 million for comparable spans, with typical service life requiring major renovation within 15 to 30 years of completion. Renovation costs frequently exceed original construction expenses, creating annual service costs between $2 and $6 million for structures that rarely achieve the longevity that Carnegie Steel has demonstrated consistently. The economic advantage of building for centuries rather than decades becomes mathematically undeniable when calculated over extended time periods. Contemporary steel production optimizes for volume and immediate cost reduction rather than the long-term performance that characterized Carnegie's methodology. Chinese steel imports, representing 30% of American consumption, often contain high sulfur content that accelerates corrosion processes. Domestic producers, competing primarily on price, reduce expensive additives like chromium and nickel that enhance durability but increase manufacturing costs. Quality testing relies on statistical sampling rather than the comprehensive testing that Carnegie demanded for every piece of structural steel. The outsourcing of steel production has eliminated the integrated control that made Carnegie's quality possible. Modern bridge builders purchase steel from the lowest bidder, concrete from separate suppliers, and fabrication services from third contractors with no single entity responsible for overall quality from raw materials to final installation. When contemporary bridges fail prematurely, responsibility shifts between suppliers while no party accepts accountability for systematic quality control throughout the entire production process. As America invests $40 billion through current infrastructure legislation to repair failing bridges nationwide, the 151-year-old Eads Bridge requires no federal funding for structural rehabilitation. Carnegie's chromium steel arches will likely outlast the modern bridges being constructed to replace structures that failed to achieve their designed service life, providing permanent testimony that American engineering excellence, supported by systematic quality control and scientific manufacturing methods, can build infrastructure that serves the nation for centuries rather than decades.